Welcome to Understand the Math. In this Calculus 1 video, we're learning how to use linear approximations and differentials to estimate values of functions and measure error. We'll start by going over the linearization and differential formulas and see how the tangent line can be used to approximate a function near a point. Then we'll work through lots of examples, including finding linearizations, checking the accuracy of approximations, finding differentials, and estimating functions and error. Be sure to download the free guided notes to follow along and work through the examples with me. Let's look at the linearization and differentials formulas and see how they're used to approximate a function near a point. Linear approximation is a method used to estimate the value of a complicated function f of x at a point x, that's this point right down here, near a point x is equal to a with a known function f of a, that's this point right here. The tangent line to the curve at x is equal to a that I've drawn down here in green is used to approximate f of x. This is the value that is used for that approximation. F of a is the y value that we know. F of x is the y value that we are approximating. And then L of x is the approximation. The linearization of f of x at x is equal to a is the y value of the line that is tangent to the curve y is equal to f of x when x is equal to a. That's just this green line that was drawn up here. This is the y value that we're talking about. The equation of our tangent line can be written as y minus y1 is equal to the slope m times x minus x1. x1, y1 is then just the point a, f of a, and our slope m is the derivative of the function at the point x is equal to a. If we plug both of those in, we get that y minus f of a is f prime of a times x minus a, and then we want to solve for y, and it's just f of a plus the derivative of our function at a times x minus a. This y value is our linearization L of x, so the linearization is just f of a plus f prime of a times x minus a. We say that f of x is approximately L of x when x is near a. When we're working with application problems, oftentimes linearization is best described using differentials. When we use differentials, we need to use a different notation than we did with linearization. With differentials, this point here is going to be notated by x f of x instead of a f of a, and that's the function value that we know. This point is the function value that we are approximating, and the approximate value is given up here by this point. When we use differentials, we focus on the change between this point here in yellow and this point here in pink. dx or delta x is the actual change in x. Delta y is equal to f at x plus delta x minus f of x, and that's the actual change in y. And then we use differentials to approximate that actual change in y with dy, which is equal to f prime of x dx. That's this distance right up here, and that is the approximate change in y. The formulas with linearization and differentials look very different, but they are doing the exact same thing. And that is approximating a function value that is near a function value that is known. We're now going to walk through two examples where we are going to find a linearization. We want to find the linearization L of x of the function at the point x is equal to a. The first function that we are going to be finding the linearization of is f of x is equal to x cubed minus 3x squared plus 4, and we are going to be finding that linearization at the point a is equal to 1. I've written down the formula for the linearization L of x, and it's just f of a times f prime of a times x minus a. So let's start with that. Let's go ahead and let's write down what that formula is. L of x is f of a plus f prime at a times x minus a. When you find a linearization, what you have to actually find is f of a and then f prime of a. Our f of a is equal to f at 1, so we just plug 1 into our function up above, and we have 1 minus 3 plus 4, and that is equal to 2. I'm going to highlight that so we can find it when we need it. Now we need to find f prime of a, so we first have to find f prime of x. So f prime of x, looking at f of x up above, is 3x squared minus 6x. And now f prime of a is just f prime at 1, and that is 3 minus 6, which is minus 3. Now we can write down L of x. L of x is f of a, which is 2, plus f prime of a, which is minus 3, times x minus a, which is x minus 1. Typically, when you find linearizations, you don't multiply this answer out because this form is useful when you use L of x to approximate a function that has an x value that is close to 1. Over here on the right, I have graphed our function f of x and then our linearization L of x. And notice that these two functions are almost identical at the point a is equal to 1. And that's how L of x can be used to approximate f of x. Let's now look at our second example. The function that we're going to be finding the linearization of is f of x is equal to sine x, and we're going to be finding the linearization at the point a is pi over 6. Just like we did with the first example, let's start by writing down our formula. L of x is equal to f of a plus f prime at a times x minus a. Now let's go ahead and substitute in that a is equal to pi over 6. This gives us L of x is equal to f at pi over 6 plus f prime at pi over 6 times x minus pi over 6. F at pi over 6 is just sine of pi over 6, and that is equal to 1/2. And we'll highlight that so we can find it in a minute. Now we need to find f prime at pi over 6, so we first have to find f prime. The derivative of sine is cosine, so f prime is cosine x. Now we can find f prime at pi over 6. That is cosine of pi over 6, which is equal to the square root of 3 over 2. And let's highlight that. Now we can write down L of x. L of x is f at pi over 6, which is 1/2, plus the derivative at pi over 6, which is root 3 over 2, times x minus a, which is just x minus pi over 6. And that's our linearization. I again went ahead and graphed f of x and L of x. And if we zoom in here, you can see that when x is pi over 6, that's this point right here, L of x and f of x are very close to the same value. Let's now look at an example where we want to determine the accuracy of a linear approximation. This example is split up into two parts. For the first part, we are going to find the linear approximation of the function f of x is equal to the square root of x plus 3 at the point a is equal to 1. When we find a linear approximation, we are just finding a linearization. So we're going to start by writing down the formula for a linearization. That is L of x is equal to f of a plus f prime at a times x minus a. Let's go ahead and substitute in that a is equal to 1. So L of x is equal to f at 1 plus f prime at 1 times x minus 1. We need to find f of 1 and f prime at 1. I'm going to start by writing down f of x. F of x is the square root of x plus 3. And because we have to take the derivative, I'm going to write this also as x plus 3 to the 1/2. Now we can find f at 1. Just substituting in x as 1, we get the square root of 4, which is 2. Let's highlight that so we can find it later. Now we need f prime at 1, so we first need to find f prime at x. This is 1/2 x plus 3 to the minus 1/2. We can write this as 1 divided by 2 times the square root of x plus 3. Now we have to find f prime at 1. So x is just going to be 1. So we have 1 all over 2 square root of 4. So that is just 1 over 4. And let's highlight that. Now we can write down L of x. L of x is f of 1, which is 2, plus f prime at 1, which is 1/4, times x minus 1. And that's our linear approximation. Now let's look at the second part. We are going to determine the values of x for which this linear approximation is accurate to within 0.1. A linear approximation is accurate to within epsilon. We use epsilon to indicate when we have something relatively small. So our linear approximation is accurate to within epsilon when the absolute error is less than epsilon. The absolute error is notated as capital E of x, and it's just the absolute value of f of x minus L of x. So we say that this absolute value is less than epsilon, and then to make things easier, we get rid of the absolute value, and we put epsilon on either side, and then we know that our function is going to be between L of x minus epsilon and L of x plus epsilon. Let's now see how this works for our example. We want the absolute value of f of x minus L of x, that is the error, to be less than 0.1. This means that minus 0.1 is less than f of x minus L of x, is less than 0.1, and then L of x minus 0.1 is on the left. In the middle, we have f of x, and then on the right, we have L of x plus 0.1. Now we're going to substitute in for L of x and f of x. L of x was 2 plus 1/4 x minus 1, and then we subtract 0.1. And then our f of x is the square root of x plus 3. And then on the right, we again have L of x, 2 plus 1/4 x minus 1, but now we add 0.1. This equation is really hard to solve algebraically, and we might not even be able to do it. So what is done in practice is that you graph all three of these pieces. The graph of the first piece is just a linearization, so it is a straight line, and I have that straight line drawn down here in green. And then the right-hand side is also a linearization, so that is a straight line, and I have that drawn in purple. And then the function that we're approximating, I have drawn in blue. The function is only going to intersect one of these straight lines. In our case, our function, the square root of x plus 3, is concave down, so it's going to intersect the green line. Let me go ahead and make this bigger so that you can see that. I graphed this on Desmos. It's a really great free graphing tool if you want to use it when you do these types of problems. And I found that our linearization intersects our function here and here. So that tells us that our linearization is going to be accurate to within 0.1 when x is between minus 1.13 and 3.93. Let me go ahead and let's write that down. So our answer is going to be minus 1.13 is less than x is less than 3.93. Our linearization then will be accurate to within 0.1 when x is between these numbers. We're now going to look at an example where we are given a function and want to find its differential. We want to find the differential dy and then evaluate it for the given values of x and dx. And then we're going to sketch dy and compare it to delta y. Just to make things easier, I've written over here in this green box the formula for the differential dy and delta y. The function that we're going to be finding the differential of is y is equal to the square root of x, and we're going to evaluate the differential at the point x is equal to 1 and dx is equal to 1. Y is our function of x, and it is the square root of x, and I'm just going to write this as x to the 1/2 because we're going to be having to take the derivative of it. Now let's write down our differential formula. dy is f prime at x dx, and this derivative is 1/2 x to the minus 1/2 times dx. So we can say that dy is dx all divided by 2 times the square root of x. So that is our differential. Now what we're going to do is evaluate this differential when x is 1 and dx is 1. So we're going to say dy when x is equal to 1 and dx is equal to 1 is just going to be 1 over 2 times the square root of 1. So that's just 1/2. And let's go ahead and highlight that answer. Now we are going to compute delta y. That is the exact change in y. And this is f at x plus delta x minus f at x. Delta x is the same thing as dx. So we can say that delta y is f at x plus delta x. So this is just the square root of x plus dx minus f of x, which is the square root of x. Now we're going to find delta y when x is 1 and dx is 1. So this becomes the square root of 1 plus 1 minus the square root of 1. So this is the square root of 2 minus 1, and this is approximately 0.41. dy is the approximate change in y, and then delta y is the exact change in y. I have placed a graph down here so we can visualize what we just calculated. Differentials are used to find the change between this point and this point. Delta y is the exact change in the y value, and we found that to be 0.41. And then dy is the approximate change in the y value, and we found that to be equal to 1/2. In this example, we are going to use both linear approximation and differentials to estimate cosine of 31.5 degrees. In part A, we are going to use a linear approximation to estimate this value. And then in part B, we'll use differentials. Over here in this green box, I've put down our formulas. Our function is going to be approximated by L of x, and then I have the formula for L of x. Our function f of x is cosine x, and this is approximated by L of x. L of x is equal to f at a plus f prime at a times x minus a. X is always the value that we're given, and in this example, x is going to be 31.5 degrees. And then a is a nearby point, or in this case, an angle, with a known cosine value. The value of cosine that we know that is close to 31.5 degrees is 30 degrees. Now what we need to find is f of a and f prime at a. F at a is cosine of 30 degrees, and that is root 3 over 2. Now we need to find f prime at a, so we first have to find f prime of x. F of x is cosine, so f prime is minus sine x. And then we can find f prime at a is minus sine of 30 degrees. And this is minus 1/2. I'm going to highlight f of a and f prime of a because we're going to need to plug those in. We can now write down L of x. So L of x is f of a, which is root 3 over 2, plus f prime of a, which is minus 1/2, and we multiply that by x minus 30 degrees. Now we want to find L at 31.5 degrees. So this is root 3 over 2 minus 1/2. 31.5 degrees minus 30 degrees. Now here's where students usually get confused. We cannot have degrees in our answer. Instead, we need to work with radians. So we have to multiply this by pi over 180 degrees. This answer then is equal to 0.852935. So we can say that cosine of 31.5 degrees is approximately 0.852935. I want to show you how good this approximation actually is. So I went ahead and I took my calculator and I plugged in cosine 31.5 degrees. And here's what I got, 0.85264. So our approximation is really good. Now we're going to do the same thing, except now we are going to use differentials to estimate cosine 31.5 degrees. When we use differentials, the notation is very different than when we used linearization. For differentials, we are going to be approximating f at x plus delta x, and I've written down the formulas for that approximation. We're going to start by saying that f at x plus delta x is cosine of x plus delta x. And this is going to be approximately, looking over here at the right at our formulas, f of x plus dy. And if we substitute in what dy is, this approximation is f of x plus f prime at x dx. X plus delta x is going to be the angle that we're given, and that is 31.5 degrees. And then x is a nearby angle with a known cosine value, and that is going to be 30 degrees. What we need to do now is we need to find f of x and f prime at x. Since f of x plus delta x is cosine x plus delta x, f of x is cosine x, and x is 30 degrees, so this is cosine 30 degrees, which is the square root of 3 over 2. Now let's find f prime at x. That is going to be minus sine x, and x again is 30 degrees, so this is minus sine 30 degrees, which is minus 1/2. And then I also realized that we also have to find dx. dx is the same as delta x, so that is going to be 31.5 degrees minus 30 degrees, which is 1.5 degrees. Now we're going to take all three of these values and substitute it in to our equation. So we can say that cosine of 31.5 degrees is approximately f of x, which is root 3 over 2, plus the derivative minus 1/2 times dx, which is 1.5 degrees. And then we need to convert degrees to radians, so we multiply by pi over 180 degrees. And we get the value 0.852935. And that, of course, is the same value that we got when we used linearization. Let's now look at an application example where we're going to find some error estimates. We're told that the radius of a circular disc is 24 centimeters, and it has a maximum error in measurement of 0.2 centimeters. We want to estimate the maximum error, the relative error, and the percentage error in the calculated area of the disk. Y is equal to f of x is the function that we're going to be calculating the error in. So in our example, this is going to be the area function. The maximum error is given by dy. The relative error is then dy divided by y, and then the percentage error is just the relative error times 100%. I went ahead and drew a circle to represent our circular disk. It has a radius r, and we're going to write down that the area is pi r squared. So we are going to be calculating the error in this area. Let's first find the maximum error. So the maximum error is going to be dA. Taking that derivative, we have 2 pi r times dr. We are told that r is 24 centimeters, and then the maximum error in measurement, that's actually dr, and that is 0.2 centimeters. And now we can find dA. So dA is 2 pi times r, which is 24 centimeters. Make sure to put units in there. And then our dr is 0.2 centimeters. And this is equal to 9.6 pi centimeters squared. When we leave pi in our answer is an exact answer. Now let's find the relative error. That is dA divided by A. dA was 2 pi r dr. I'm just looking right up here for that. And then we divide it by A, which is pi r squared. So one of the r's cancels, the pi's cancel. So we end up with 2 dr in the numerator and then r in the denominator. We have 2 times dr, which is 0.2 centimeters, all divided by r, which is 24 centimeters, which gives us a relative error of 0.0167. The last thing that we need to calculate is the percentage error. So the percentage error is just our relative error, 0.0167 times 100%. So this is just 0.0167 times 100. And that gives us a value of 1.67%. So this calculation tells us that if the error in our radius is 0.2 centimeters, the percentage error in our area is 1.67%. And that's it. You've learned how to find linearizations, use differentials, and estimate error in applications. You also practice determining when a linear approximation is accurate and how differentials can give quick estimates for changes in functions. To really master linear approximations and differentials, make sure to work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.